is going to be on, I will say, you know, related to the exam. Okay. Remember, for the exit tickets or the quizzes, they will not be announced. You will not learn anything about the questions until you access the recorded lecture. Okay. Then embedded in the lectures, you are going to find these exit tickets or quizzes. All right, thank you. And now we are going, like we did study in chapter 3, two-dimensional motion and like vectors, how we're going to deal with vectors. And today we are going to introduce one of the most important, I would say, application, which is two-dimensional kinematics. Okay, now two-dimensional kinematics means that my object will not move along the x only or along the y only. It will simultaneously move along a path like related to xy. Then it's going to be in xy plane. And the approach that we are going to use is we are going to split the motion into two motions. One of them is along the x-axis, the other one is along the y-axis, and we're going to deal with one-dimensional problems in each. Now, we will learn something about projectile motion, like the basic equations, what we should use, and you're going to find that we will not use something new. These are the same exact equations that we did use, and the reason is going to follow. Zero lane launch angle, something like my prefer is going to be horizontal launching. Okay, then zero launch angle means horizontal. Okay, because we are measuring the angle from the positive x-axis. And then I will say this is a special case. Okay, now we are going to move also to general launch angle. Okay, and we will talk a little bit about some of the characteristics related to this motion. Now, just here, a reminder that if I have an object moving with constant velocity, this is what I'm going to use. The acceleration is 0. Then v at any time equals the initial velocity, and its x is going to be x0 plus v0t. I like always to write this as delta x equals v0t. Okay, then it is just only one equation. And for the constant acceleration motion, we have these four. Maybe I told you, like here, I like to use this one, delta x. This is like the average velocity divided by, multiplied by time. Then, okay, this is again, this is my modification to this. Okay, then you have, if you are going to talk about constant acceleration motion, you need to use the equations to the right. If you need to talk about constant velocity motion, means the acceleration is 0, you need to use the ones on the left. Now, Galileo was the first to describe the projectile motion accurately, and he did show that it could be understood by analyzing the horizontal and the vertical component of the motion separately. And here we are in this diagram, we are showing you like two balls. One of them was directly dropped. Okay, then it's dropped, it's not thrown. Okay, and the other one was fired horizontally. Okay, now if you look at the vertical motion, you're gonna find that they are really the same. And the reason is because the acceleration is the same. Then regardless if the object was, okay, I will say thrown, I will say dropped or thrown with, I will say a velocity, the vertical motions, they're going to be the same. Okay, their horizontal motion, of course, is different because we will find that for the yellow one, it has a horizontal velocity, and therefore it's gonna, like, its distance, like here horizontally, is gonna grow. And this is the reason why now when it hits the ground, it's going to be away by that distance. Versus the pink one, it doesn't have any horizontal component, and this is the reason why it will hit the same exact point from where it was launching. This is here, we are talking about horizontal launching, okay? This one. Initially, my velocity has only one component, and I like here before this, okay, let's see here. Okay, to tell you what's going on, I want to use the general first, so that just to show you why I need to split the velocity into two. This is the most general projectile. Then my object, let's say, was here, and it will leave with a velocity v0. And then here there is an angle. I don't want to say theta 0. We can say, because the theta is going to change. But let's use theta. Here I will say there is a component for its velocity, which is v0 cosine theta. And this is v0y equals v0 sine theta. Now, one of the things that I want you to know that these really velocities, they're gonna change all. One of them is gonna change based if I have acceleration or not. I mean both or one of them is gonna change. Now, for the horizontal, you can see that here. What if my let's say horizontal like my projectile was horizontal. We said that this is theta equals 0. And this is the reason why v0x is going to be v0 times cosine 0, which is 1. And then this is going to be v0. And v0y is going to be v0 sine 0. And this is going to be 0. Then if my object was not general, it was horizontal, this means that this angle is 0, right? This is the x-axis here. And it is making 0 with the x-axis. This is the y. And this is the reason why I will get this. Now, I will, in my solutions, you will see that initially I will always have that type of like 4 cells here. I will list the velocity v0 in meters per second, and then it's theta, okay, whatever it was, and then I will say this is v0x and this is my v0y, okay, and then you're gonna find them. This one is gonna be v0 cosine the angle, and that one is gonna be v sine theta, okay, and this is gonna make it like for you, yeah, you know what to do exactly, okay. Now, if my object is actually fired horizontally, you're gonna find that the x component will not grow. Then v0x will not change. Why it will not change? Because there is no acceleration, okay? A equals 0. Versus, you know that the vertical component here is gonna start from 0, but it will grow. It will increase. Why it will increase? Because now the acceleration, this yellow, is in the same direction as the velocity. And remember, we did say that this before, if they are both velocity and acceleration are in the same direction, then I would say the velocity is gonna increase, or speed increases. Now I will say here also, okay, then I can use the constant velocity equation, okay, for the horizontal motion, And I can use the set of equations for the vertical motion, but in these here, we have also v0 y equals 0. And I will make x and y so that I differentiate between the two motions, okay? I don't want to give you a set of equations for horizontal and then a set of equation for the general. I will use my own set of, let's say here, as I said, my equations, the one that I did use. In the case when it is horizontal, then you are going to get your v0y is going to be 0. Then you don't have to maybe two sets of equations. Now, I will say also here the time of fall is only affected by gravity. No matter how fast the ball rolls off the table, it will still reach the ground at the same time as the ball that is dropped. Okay? And it was demonstrated here. See? It is really, and I can also, because this is a picture, I want to show you this in, what is my YouTube here? Okay, with my YouTube, when I go my library, when I go to my physics, I have it here. This is.
Consider the trajectories of two softballs. One was dropped, and the other was given an initial horizontal velocity of 2 meters per second. What is similar about the two paths? Look at their vertical positions. During each flash, the heights of the two softballs are the same. Because the change in vertical position is the same for both, their average vertical velocities during each interval are also the same. The increasingly large distance traveled vertically by the softballs, from one time interval to the next, shows that they are accelerated downward due to the force of gravity. Notice that the horizontal motion of the launched ball does not affect its vertical motion. A projectile launched horizontally has no initial vertical velocity. Therefore, its vertical motion is like that of an object dropped from rest. The downward velocity increases regularly because of the acceleration due to gravity. You can see here separate motion diagrams for the horizontal and vertical motions. The vertical motion diagram represents the motion of the dropped ball. The horizontal motion diagram shows the constant velocity in the x direction of the launched ball. This constant velocity in the horizontal direction is exactly what should be expected because there is no horizontal force acting on the ball. In this figure, the horizontal and vertical components are added to form the total velocity vector for the projectile. You can see how the combination of constant horizontal velocity and uniform vertical acceleration produces a trajectory that has a parabolic shape.
Alright, then this is really related to that motion. And here there is a multiple choice question. From the same height and the same time, one ball is dropped and the other ball is fired horizontally. Which one will hit the ground first? And of course, we have answered that one. It is both of them, they're going to hit at the same time because they both have the influence of gravity, and then they have fallen from the same height, then they will hit the ground at the same time. Okay, is that also true if there is air resistance? Okay, of course, this not gonna be the same. In the previous problem, which ball has the greater velocity at ground level? If I have, I will say one of them is fired and the other one is gonna be just dropped. Of course, the fired one is gonna get more velocity. Okay, because it has the two components. All right, now basic equations here, ignore air resistance. Then in all our problems, we're gonna assume air resistance is ignored because this is gonna complicate. The air resistance should depend on velocity. It should depend on the shape, on the surface area of the object. And it has to do like so many details that they're gonna be, and this is the reason why we're gonna ignore it. Now G, I will not use 9.81. I will use negative 9.8, okay? And that one is negative because it is downward. Also, we're gonna ignore the Earth rotation. And I will say this is the acceleration that we are going to use, okay? The acceleration is independent of the direction of the velocity because it is always what is really causes this acceleration. It is the force of gravity, and the force of gravity, it is always towards the center of the Earth. Now, zero launch angle here. Launch angle is the direction of initial velocity with respect to the horizontal. Then here we might have that theta greater than 0, less than 0, but also we might have that V0 equals 0. Now let's try using it. Here, like in this figure, we have a diver running 1.6 meters per second, dives out of horizontally from the edge of a vertical cliff and reaches the water below 3 seconds later. How high was the cliff? How far from the base of the cliff did the diver hit the water? Okay. Now remember, draw, choose coordinates, identify knowns, identify unknowns, and I will say work with X and Y separately. This is my X, this is my Y. Okay, now, and as I said, like always, this is my initial. Now, the first thing, as I told you, I usually do the velocity components. I want to make always my method standards. Okay, then V0 was 1.6. It was horizontally, then theta is 0. V0x is 1.6 meters per second. The reason that is V0x, it is V0 cosine 0, and cosine 0 is 1. And for that one, V0y, it is V0 sine 0, and sine 0 is 0. All right, now in order for me to how high was the cliff, okay, anything that is asking about the vertical, you're going to use the vertical equations. But remember, you have an option. Now in this one, it was asking about how high. Then I know that I have V0y as 0. I know that I know the acceleration. You can call it AY. And I know that T is 3 seconds was given. And I'm looking for delta Y. Now, if you check all the equations, the 4 equations that we have, okay, I'm going to write them here now. Okay, then this is the one that I did choose, which is going to be the one that is going to give me the correct solution. All right. Okay, these are the equations. And based on what I have, the 4 variables here, I did choose that this one is going to be my solution. Now, one thing that I want you to pay attention to is your acceleration here should be negative. Now, because the question is asking about the height of the cliff, then you might think, okay, I need to consider 9.8. This is not correct. I am measuring first the displacement of the swimmer, which is going to measure the height of the cliff. Then the displacement of the swimmer is the negative 44.1. Okay, and it equals to the height of the cliff, which you are going to consider 44. Okay, if you have your solution here, giving me g, or like, you know, the acceleration here negative, not negative, positive, you're gonna have it wrong. Now for the horizontal, I know that I have only that equation, delta x equals vxt, and then my here is going to be only 3 and 3 cells, and I will have the v0x, which is equals, of course, the velocity at any time. I have the time and delta x, I'm looking for it, then delta x equals Vx times t equals 1.6 times 3, and delta x is going to be 4.8. Now, this following one, I will leave it for you as the what is called the exit ticket for chapter 4. Okay, and that one, you will find a link on Canvas that is going to lead you to Gradescope. You are going to submit this equation as, I would say, testing your understanding. It will be exit ticket number 4, which is related to chapter 4. Now you drop a package from a plane flying at constant speed in a straight line without air resistance. The package will lag behind the plane while falling, remain vertically under the plane while falling, move ahead of the plane while falling, not falling at all, and of course is gonna be remain vertically under the plane while falling, because it's gonna be the same, I will say, it's gonna be the same horizontal speed, because they have both the same horizontal speed. Okay? Okay. Now, for the general launch angle, we have an object that is launching at an angle of theta 0 with a horizontal, and the analysis is similar except that the initial velocity will have a vertical velocity component. Okay? And I will show you how to solve this one here. I have a football that was kicked at theta equals 37.0 and v initial 20 meters per second. The question is asking about what are the components of the initial velocity, what is the maximum height it achieves, how long does it take the ball to return to the ground, what is the total distance traveled in the x direction, what is the velocity vector at the maximum, what is the acceleration vector at the maximum height. Okay, now initially I will first draw, and I will have, this is, it was, okay, sorry, let me have here more space. This is draw, where you have, this is the general. Okay, I'm gonna have my x and y. This is 37, and this one is v0, 20 meters per second. Okay, this is the highest position, and this is when it will land. Okay, as I said, the first thing I'm gonna do is, usually I will, even if the question was not asking about the components of the initial velocity, because most of the time you should, calculate both. Okay, then here I said my initial velocity is 20, the angle is 37, v0x is 15.97. I have calculated that as v0 cosine 37, and this one v0 sine 37. Now in the second part, they are asking what is the maximum height. And here I will say something very important is this is a keyword to tell you that Vy at the highest equals 0. Okay? Then whenever it's going to talk about maximum height, you know that Vy equals 0. And then I entered my knowns and unknowns. My V0y is 12.04. My Vy is 0. Acceleration is known always at negative 9.8. And then I did choose my equation among the equations, and this is the best one. And I have calculated my delta y. Now I want to calculate what is the time for it to return to the ground. This one also, it has, like we did with the free fall, it has so many I will say options in the solution. The one that I'm using is that when it will start here, okay, the vertical is gonna be 12 meters per second. Now, since we don't have a resistance and we have completely symmetrical, then here I can say this is negative 12 meters per second. Or I can calculate the time from here to here, and then I multiply it by 2 because, again, the motion is symmetrical. There are many other methods. Okay, and then V0y is 12, Vy is negative 12, and then I will say A is negative 9.8, and from that I did choose this equation. It is the best, and this is the reason that I did use it. Now, total distance in the x direction, like we did in the previous question, you have the velocity along the x-axis multiplied by the total time, and this is going to give you the total horizontal distance. Now, they are asking about the velocity at the maximum. At the maximum, I have Vx equals 16, but Vy is 0, and this is the reason the velocity will be 0, no y component, and the acceleration is going to stay negative 9.8. Now, a projectile is launched from the ground at an angle of 30. At what point in its trajectory does this projectile have the least speed? At the highest point, because the velocity component of y is going to be 0. All right, because all other points you are going to have the two components, they will be participating in the value. But here it is just the y, it's just the x component. Okay, I don't like actually to use any, like then this one, if I asking about the range or the horizontal, I don't want you to use any derived equations, but just here we're showing you this equation to show you that we have that, like this was derived using the two equations here combined together, and we are using it just to prove that we are going to have the maximum range when theta is 45. Okay, then the range is maximum when theta is 45. And at that moment, our maximum can be calculated as this. Okay, I don't want you to use any of these equations that they are going to be the, I would say, derived equations. Okay, I want to show you here. I want to show you this here, this FET, okay, which is the projectile motion 1. Yes. Okay, just here, like I will have, let's, this is, and then this is 0. Okay, I want to maybe make my angle, let's say 10, and fire, and then make it 25 and fire. See, it is increasing. Fire. This is 50 now. Look here, that, okay, and then here it will start decreasing again, because at 45 is gonna be the maximum. Okay, one more thing I want to show you here is, let's say I will have this as 60 and fire. Okay, one, and the other one I'm gonna make it 30 and fire again. Okay, they are going to meet at the same point. Okay, and this is the reason why is I will say complementary angles, we call them, the ones that they have, and of course it is based on the equation, but it's gonna be related to the equation that we are using. Okay, now this is a multiple choice questions that is asking you about what is the maximum height. And here also we are trying to imagine that we can have any ponds in here, and we are asking about which one has the longest time. Remember, I did say this before, that since we like that the time is going to depend only on the vertical, and since it is h always, then they all have the same hang time. This one is very interesting. You have to aim above your target to hit it, because gravity is causing your projectile to fall. And what if your target is falling too? If the target drops at the same time you release your projectile, where should you aim to hit it? And just here, I want to show you the video. I think I have it here. Here we have I have a stuffed monkey that is suspended using an electromagnetic. And I have a golf ball that is going to aim at that monkey, and at the same time is going to cut off the electricity. Then once it's going to hit, the stuffed monkey is going to start moving back. Here that, or can you see they're gonna hit? Okay, this is another one, like it's gonna midway, and then okay, and just here. No animals were hurt in this. Okay, then we'll say here the stuffed monkey was just suspended using an electromagnet, which when I will, cut the electricity is going to fall, and the golf ball aimed directly at the monkey cuts the power when it fired. Thus, the monkey begins falling at the same instant the gun fires the gun ball. The projectile and target meet in mid-air, and this is really because I will say maybe some of the people they're gonna think, okay, the ball will go over the monkey's head due to its fast speed. However, gravity accelerates all the objects downward at the same rate, which means they will meet and exactly at the same point, and the ball was shot even faster. You will have the same, the same result, but it will still hit it, but higher above the ground. Okay, and this is the summary of chapter 4. Components of motion in the XY direction can be treated independently in the projectile motion. The acceleration is negative g. If the launch angle is 0, the initial velocity has only x component. The path is